Hi, in this video we'll go over an overview of software testing. So here's an outline. We'll first start with terminology and go over some of the basic terminology in software testing. Next we'll look at various testing activities, followed by different types of testing. So let's start with a discussion of some of the famous problems that were caused due to software testing. The first one that's famous in software engineering history is the F-16 fighter plane crossing equator using autopilot, and the result was that the plane flipped over. Now why did that happen? It's because of reuse of an autopilot software from a rocket. So reuse is good, there's no problem with that, but then the software that was reused was that of a rocket, where the parameters are different, and a rocket flying over the equator and flipping didn't matter, whereas for a fighter plane it did matter. Another big incident was the Therac 25 accidents that happened during the 1985 to 87, and this in fact was one of the most serious non-military computer related failure in terms of human loss, and at least 5 people died in those accidents. And the reason over there again was the software that was being used, and it was a concurrent programming related error. Another one is the NASA Mars Climate Orbiter that was destroyed when due to incorrect orbit insertion, and this happened in 1999. And here the reason was later on found to be a unit conversion problem. So the problems could be really small and minor, but the kind of effect that they can have can be drastic, especially when we're dealing with critical systems and systems where humans are involved. So that's the reason software testing is so important, and that's the reason we're discussing it and looking at different tools and methodologies to make sure quality software is produced. So we'll start with the terminology. The common terms that we hear are failure, error, fault, and validation. And all of these have a different meaning. They're all related. They're all related to software testing and failure, but then there's subtle differences between these terms. So failure is basically any deviation of the observed behavior from the specified behavior. So we know that if there is a system and it's expected to behave in a certain specified way, and if there's any deviation from that expectation, then that's a failure. Erroneous state, also known as error, is basically the system is in a state where if it further processes or continues with the processing, then the system can lead to a failure. So the failure has not occurred yet, but the system is in a state where proceeding to the next step will lead to a failure. The third terminology that we commonly see or hear is fault, also known as bug or defect. This is basically the mechanical or algorithmic cause of an error. So anything that's in the program, in the code, or some kind of a mechanical fault or a hardware fault that could cause an error and eventually a failure is what is a fault, bug, or defect. And finally, validation is basically the activity of checking for deviations between observed behavior and its specifications. So it's basically this whole process or activity of confirming that the system is behaving the way it should behave. So with that said, there's a picture shown here. I'll give you a few seconds to think about what is this? What do you see? And again, thinking in terms of the terminology that we just discussed. Is it a failure, an error, a fault, a bug, defect, validation? What is this? Now, the question is hard to answer if I don't specify in the first place what is the desired behavior for the system that I'm showing. So we need to know what is that desired behavior first before being able to answer the question. So always that specified behavior is to be known. Now say the specified behavior is that it's a train track, and a train or an engine of a train should be able to move from one end of the track to the other end successfully. So, say that's the specified behavior. Then what is this? What do you see now in the picture? So in this case, this is an erroneous state or an error. The reason for that is that a failure hasn't happened yet. We see that the engine is still on the track. So nothing bad has happened yet. So far, it's behaving as per the specified behavior. It's able to move on the track from one end to the other. But then it is an erroneous state. It is an error state. And the reason for that is if this engine proceeds any further from where it is now, then it's going to result in a failure. So this is an erroneous state or an error. Now what do you see here? So basically what we see is a few workers trying to put the track together, and due to some reason they've put it together in this manner. So this is an algorithmic fault. So again, it's like our coding errors or errors in a program where which could lead to errors and failures later on. So this is an example of an algorithmic fault where while the tracks are being constructed, it's being constructed or put together incorrectly. What do you see in this picture, and what is this? Again, let me give you a couple of seconds to think about it. So what you see here is again the same train track, and the workers are working on it, and maybe some kind of a natural calamity like an earthquake happened, which so initially probably the track was put together properly, but then the earthquake caused the tracks to break and move apart. So this is an example of a mechanical fault where it was fine at the beginning, but then later on, due to some mechanical issues, it got into this fault state. So to give you some examples of faults and errors. Now faults could be there in a number of different places. So one of the first ones that we discussed was algorithmic faults, that's shown here, which is basically coding related issues. Things like missing initialization, a variable is not initialized correctly, incorrect branching conditions, or maybe some branching conditions are missing, certain cases are not taken care of when the conditions are being defined, or a missing test for null, so which means you're trying to access a variable that doesn't hold any value and it has a null value. So these are some of the things that could happen in our algorithms, and they're called algorithmic faults. The other kind of faults that we see are interface specification faults. So this is when there's multiple systems or multiple classes or multiple interfaces talking to each other, interacting and communicating with each other, and there could be a mismatch between what a client needs and what the server is offering. So basically, say one class is trying to access some data or information from another class, the way in which this first class is trying to communicate with that second class may be off. So that's an interface specification fault. The other kind of faults are mechanical faults. These are the ones that are hard to find, and if it's hard to find, and then eventually hard to fix. Things like the operating temperature of the equipment is off, it's outside of the specification. So things like, say there is an ATM machine that's sitting outside a building, and there's a certain temperature that it operates under, and if the temperatures go outside that range, then that's a mechanical fault, and it might cause the software to fail. Things of those kind that are beyond the software itself or the code itself, but it's related to the mechanics or the hardware, those are called mechanical faults. And then so those are all faults, and then we have errors. So basically, what are the kind of things that are would be treated as an error state, and then if we proceed from that point on, if the program proceeds with the execution, then it might lead to a failure. So those examples of those would be, say there is a null reference, And if we continue with using that null reference, or if the program execution continues with the execution using that null reference, then that could lead to a failure. Similarly, concurrency related errors, when there's a shared resource and if there's multiple processes trying to access that same shared resource, then that could cause issues. Exceptions, when some exception conditions happen, say the input provided is not in the correct format that the program is expecting it to be in, so that could be an exception. So all of those are examples of errors or error states, and then continuing processing from that point on could lead to a failure. So that was to give you a sense for some examples of faults and errors. So now that we understand the terminology of what is errors, failures, and faults, now how do we deal with them? And that's what we're really concerned about. So let's look at some ways in which we could deal with them. So broadly, at a high level, this first one is modular redundancy. So basically, one way to deal with failures is by providing a modular redundancy. So say if one particular module fails, then we provide or we have a backup module ready, which is in general redundant, but in case of a failure, then it can get used. So that's what you see over here. There's multiple tracks. If the first one fails, then we can use the second one. So that's called modular redundancy. Often we have to do this with servers. There's multiple servers, so that if one of them fails, then and all of the information and data and operations are replicated on them, so that if one fails, then we can go with the alternate one. Another way is declaring the bug as a feature. I'm just joking that doesn't really work. Well, can we declare bug as a feature? Maybe in some cases we can, but in most practical cases that doesn't work. Patching, yeah, that does work. We could provide patches. So basically, once the issue is found, then we fix it and send out a patch to all the users. So that works, but it works for non-critical systems. That's not a good idea for safety critical systems, where the safety of the users who are using it is of utmost importance. So patching could work for these non-safety critical systems. Testing is our other way to handle failures, and that's a good way, and in most cases that works, but it's not a trivial task. So basically, if we had performed testing on the track that we had with a few testers trying to simulate the behavior of the engine that is going to move from one end to the other on the track, then the issue with the broken track could have been found. So testing is one of the common ways to deal with it. So to broadly classify these different ways in which we can deal with faults, there's three different ways in which it's done. Fault avoidance. So basically, we want to avoid faults in the first place. We want to create our software in such a way that as we are creating it, we don't even introduce these faults, be it algorithmic or mechanical. So this happens even before the system is released. So as you're building the software, basically the idea is to use a methodology or a process that reduces complexity and ensures high quality software. So basically, the idea is to follow a proper methodology and process, use configuration management to prevent inconsistencies, to use proper source controls so that different versions of the source code is maintained and there's no inconsistency, to apply a verification process at the design and algorithmic levels so that all of the algorithmic faults are taken care of. And basically, verification is this process of ensuring that the observed behavior is the same as the specified behavior. And then user reviews, so basically reviewing design, reviewing code, and this is, we're not executing the system here. The system is not running. We're just talking about statically statically analyzing the code, statically analyzing the designs, and having some other person other than the designer or the developer review them for identifying any potential faults. So all of these are fault avoidance techniques, that is, even before the system is released, even before the system is under execution, can we reduce the number of faults and issues and ensure quality. The second technique is fault detection. So this is once the system has been built and once it is running, then what do we do to handle faults or to deal with faults? So there basically our goal is to detect faults, to find them, and the way that can be done is through testing. So basically an activity to provoke failures, and we do this in a planned manner. We have to come up with different kinds of activities and test scripts so that we can try and provoke failures, think of all possible inputs that can be provided to the system, and then make sure the system is behaving the way it should. The next is debugging. So this is once we have found a fault, it's a way to actually remove those faults from the code. So that involves, once the fault has been determined, it involves stepping through the code and figuring out where exactly the issue is, where exactly is that algorithmic fault or code in the error in the code that needs to be fixed. So that's debugging. And then the third technique is monitoring. So this is basically to monitor the system, typically also used during debugging, in some way track all of the user activity of the system, and store that information, any kind of state information about different variables, different objects that are being used in the system, so that we can look for any strangeness that might be causing the faults. So fault detection involves this testing, debugging, and monitoring, and all of this can happen only while the system is running. So we need an up and running system in order to be able to do this. The third technique is fault tolerance. So this is basically now, say a failure has happened. Now how do we recover from that failure? And typically this is once a system has been released. So this is where things like exception handling and modular redundancy come into picture. So basically the failures have happened, but then can we build a system that is so tolerant that the user won't even realize that a failure occurred, or it won't affect the user? So exception handling does that. It's basically looking for these exception cases and providing an alternate way to deal with it. And modular redundancy is again providing an alternate or backup module that will take care of that basically comes into play when a failure occurs. So basically at a high level, these are the three ways to deal with faults, and they happen at different phases in the life cycle of software development. Fault avoidance, that happens while the system is being built, the system is not released yet. Fault detection is once the system has been built and it's up and running. And then fault tolerance is once a system has been released and a failure has occurred. Now how can we handle or recover from the failures that have occurred? So here's a taxonomy of these various fault handling techniques that we just looked at. Basically the three were avoidance, detection, and tolerance. Under avoidance, the idea is to follow a good software engineering methodology and process, follow things like configuration management to handle the different configurations of the software system and make sure we don't get into inconsistencies, and verification. Fault detection involves testing and debugging, and within testing again there's different types of testing like unit testing, integration testing, and system testing, and we'll look at them in detail in later videos. And then under fault tolerance, there's things like atomic transactions, modular redundancy, exception handling. Atomic transactions is basically if there are transactions that are related, and if one of them fails and if it's going to have an effect on all of the other ones, then they need to be performed in an atomic way, so that if one fails, then all of the other ones are also rolled back. So these are some of the fault tolerance techniques. So here's some observations. So we clearly we see that testing is very important, and that's one way to basically find faults once a system has been developed. But then also I must tell you that it is impossible to completely test any non-trivial software system. And the reason for that is there's practical limitations to it, and there's theoretical limitations to it. Theoretically, it has been proved it's not possible using the halting problem. There's practical limitations. It takes time. It takes a lot of time to do testing, especially if you want to test all possible cases. And again, we're talking about non-trivial software systems here. So it's prohibitive in time, and it's also prohibitive in cost. Testing is costly. It involves a lot of money and resources. You need people, testers, who have a good understanding of both the application domain as well as the solution domain of how the software system has been built, so that they can think of all possible test cases. So all possible test cases need to be generated. So that's the reason it is a hard problem. Also, Dijkstra has shown that testing can only show the presence of bugs and not the absence of bugs, because in order to show the absence of bugs, you have to completely test the software, and there's no way we can ever say that we have completely tested the software. So testing is not free. So in any kind of testing activity, it's important that we define what our goals and priorities are for that software system. So again, we go back to what is that specified behavior, and what are some of the critical features in there that are a priority that need to be tested first. So that needs to be defined, and all of the testing activity is basically guided by that. So testing does take creativity. So like I said, one must have a detailed understanding of the system, both application and the solution domain. And this tester also needs to have knowledge of all possible testing techniques, and testing techniques for different languages, different software platforms, and different frameworks. So basically, and once they have a knowledge of all of those testing techniques, they also need to have the skill to be able to apply those techniques. They should have the skill to think about those different test cases, think out of the box, think of the edge cases, and all of those scenarios that might rarely occur but could occur, and does the system behave correctly in those situations. Also, it's well known, and it has been seen that testing is done best by independent testers, not by the developers themselves, or not by members of the development team themselves, for obvious reasons, because when we develop software, we have a certain mental attitude towards it, and we tend to test the program in a certain way, and somehow the programmers have that bias, and they stick to that same kind of data set and tend to test their program with that same data set. And it always, the program would work with that, but then there are these other cases that a programmer is not able to think about because of this mental bias. That's the reason it's always a good idea to use independent testers, and you might have seen that from your experience as well. A program often works just fine when you test it, but then the moment somebody else tests it, that's when all of the issues begin. So that's the reason we always, there's in the industry, in large software teams, there's always a separate subgroup or a testing team, or a software quality team that handles all of the testing. They are those independent testers who are not involved in the development. So with that said, so we looked at the terminology, we understood what are some of the different ways in which we can handle faults and failures. So the next thing we'll look at is what are some of these testing activities. So typically our testing, software development in general starts with client expectation. Right? So we receive our requirements from the client, we understand what the client expectations are, and based on that we come up with a requirements analysis document. So a detailed requirements document which could be a result of back and forth discussions with the client, making sure that the client's expectations have been understood. Now, once we have that requirements analysis document, then that's when the team starts designing the system, and they come up with a system design document. And here we're talking about a high level design, a high level design of the system. So once that is done, then we get into object design of the system. So what is produced is called an object design document, and this is basically a detailed design. So from the high level design, now we get into more details of what are the different objects and how are these objects interacting with each other, and so on. So this first one here is a high level one where we're just thinking about the application domain, not so much about the solution domain or the technologies being used or the platform. It's just about thinking about the application. Once we get into the detailed design, that's where we start thinking about the solution. So these top 4 activities are what are happen in a regular software development life cycle. Now, specifically related to testing, if we talk about the testing life cycle, the testing life cycle starts with unit testing, and that's what you see over here. So unit testing can be done along with object design. So planning for unit testing begins with object design. Once the object design document is prepared, that basically is the input for unit testing and to start planning it. After unit testing, so unit testing is basically testing the individual components or the individual objects and making sure that they are behaving the way they should be behaving. Once that's done, then the next step is integration testing. So this is basically our multiple subsystems interacting properly with each other. So now here we are talking about multiple objects, and are they interacting with each other the way they should be doing. And then after integration testing is done, we get into system testing. So this is the overall system, all of the subsystems put together forming the entire system, and is the entire system behaving based as per the requirements analysis document. So again, the integration for the integration testing, it's the system design document, the high level design that's the input to integration testing. And for system testing, it's the requirements analysis document that's an input to system testing. So it's basically the high level overall requirements of the software system. Are they met? Are they being performed correctly? Is what we're looking for in system testing. And then the final step is the acceptance testing, which is basically now the system has been built, tested, and delivered. It's on the client side now, and are the client's expectations met? That's what is tested for in acceptance testing. So the client expectations is the input for acceptance testing. And as you can see, this is the phase, the client expectations and acceptance testing, those are the 2 activities that are on the client side. Everything else is on the developer side. Unit testing, integration testing, system testing, all of them are done on the developer side. Okay, so those are broadly our testing activities, and now we have our testing, software testing life cycle, which is basically unit testing followed by integration testing, followed by system testing, followed by acceptance testing. So let's go over an overview of these different types of testing. Unit testing, like I mentioned earlier, the purpose is to test individual component, and that individual component could be as small as a class, it could be one single class, or it could be a subsystem. And this is typically carried out by the developers. Whoever is programming or writing the class is the person who would be unit testing that particular unit. And the goal here is to confirm that this individual component is correctly coded and carries out the intended functionality, whatever functionality it's supposed to provide. So that's the goal. Integration testing is basically, now we are dealing with groups of subsystems. Now we have a collection of subsystems, and all of these put together will eventually form the entire system. Our goal here is to see if these subsystems are able to talk to each other the way they are supposed to, based on our high-level design of the system. Now this is also carried out by the developers. Here our goal is to test the interfaces. We're testing the interfaces between the subsystems. Our third type of testing is system testing. So here we are testing now the entire system. This is also carried out by the developers. Here we want to make sure that the system meets all of the requirements, both functional and non-functional. Now when I say functional requirements, what I mean by that is requirements that are related to the functionality of the system. What is it that a system is supposed to be able to do? All of those operations are called functional operations. Now non-functional requirements are basically other kind of things other than the functionality, things like how well is it expected to perform, how quickly is the system expected to provide answers. So say for example, if it's a search engine, then what is the expectation? Is the results should be returned in less than 1 second. So those kind of things are non-functional requirements. There could be other non-functional requirements related to security. We want a secure system. One of the popular non-functional requirements these days is usability. We want a system that's usable. So requirements are classified into these functional and non-functional, and when system testing is done, we're testing for both of them, both of those kind of requirements. The last one is acceptance testing. So this is the one that's done after the system has been delivered by the developers to the client. It's carried out by the client. That's key over here. All of the other ones are carried out by the developer, but the acceptance testing is carried out by the client. And the idea is that they would try out all of the typical transactions on site, and it's basically trying it out to make sure that their expectations are met, and to make sure that the system is ready to use, and that's when the developers get paid, or the software development group that took up the project gets paid. So it's basically to ensure those requirements have been met. So this video, basically the idea was to provide an overview, understand the terminology, understand what different types of testing are, and then in future videos we'll go over each of these different types of testing individually in detail. Thank you.